Hi, everybody. So we're gonna work on lab 1 today. We have a few minutes before we start class. If you want to go to Canvas and download lab 1. I also just uploaded the table for hex, decimal, and binary equivalent, so it helps you through the exercises today. Unlike the other weeks, we are not gonna program in C++ today. We're gonna do that starting next Thursday. So if you can download the lab 1, we'll go through it together, and then also the table. So I'll start in a couple minutes, give you some time to check out Canvas. Thanks, Albert. So as I mentioned in the last session, when I go into full screen share, sometimes I might not see your chat question. So if you have question, please unmute and ask anytime. And then at the end, I'll also reserve some time to really go over some of your questions. Albert has dropped in the files in the chat if you haven't gotten a chance to look at Canvas yet, but these are also available on the lab 1 page in Canvas. Yes, Yukai, Zoom now requires password, so that's part of the security updates that Zoom has implemented. They also recently implemented waiting rooms, so I opt out on that, but in September, they might have to push that through the client end. So I don't know if we have to use waiting room or not, but right now we don't. Yeah, unfortunately, I cannot disable the password option for larger audience because this is something that Zoom require. So that way, people are not part of that group can't just jump into the session and Zoom bomb and other things. So, but yeah, sorry about the hassle. I know Confer Zoom would still require password because ultimately Confer Zoom is a license of Zoom. I'm using Zoom Pro instead of Confer Zoom because when I push stuff through Confer Zoom, it actually changed the password every time, and it's a a lot of tedious stuff with administration. So, but for now, we're gonna try to use this with the password protection. I think everybody's on at 6:01, so I'll go ahead and get started. Welcome back. We had a session on Tuesday. We went over Unit 1 assignment. Today, I'm going to hit the lecture for the Lab 1. Unlike the other weeks, we are mainly going to go over the question and answer for Lab 1 today. So next Thursday, we're going to start doing a little bit of programming in C++, tying back to the concept that we're going to talk about next Tuesday. So as you complete all your activity this week, hopefully by today or tomorrow, what I'd like for you to do is take a look at the next chapter, and you can find that on the course plan schedule. And I will open the next module on Monday so you can take a look at the content, but look at the book and kind of do a little bit of reading. It's not too long. It's pretty simple. So I'm gonna go ahead and share screen real quick, and then we'll talk about, the notes and the actual assignment. So if you have the notes downloaded from last time, you can open that up. If you haven't gotten it downloaded, you can also go download it. And there are times that we're gonna jump back and forth between assignments and notes, okay? So I'm gonna do the full screen share here. So we left off, I think, on Tuesday, we finished up with addition and subtraction using in binary. So we did a little bit of the binary arithmetic. Now we're going to start with the multiplication. And as I mentioned last time, we don't usually do this manually all the time, right? But we want to understand the concept on how to do the calculation. So, in the first part, it talks about binary multiplication, and it gives you the table for the binary multiplication rules. This is very close to what you see in decimal number. So when you have 0 times 0, you would get a 0 as output. When you have a 1 times a 0, you would get a 0 as an output. When you have a 0 times a 1, you would get a 0 on the output. So anytime that we multiply by 0, right, the 1 with the 0, 0 with the 1, 0 with the 0, we get a 0 as the output. And then a 1 times a 1 is going to be a 1. And the way we operate the multiplication is the same practice as we would do in decimal number, which is our base 10 counting number. So maybe in 2nd or 3rd grade, your teacher in elementary school had gone over, or an adult had shown you how to do the multiplication. Same technique that we're going to apply here. So what we're going to do is we're going to start from the right value here in the 2nd row. And we're going to take that 1 and we're going to multiply it by the 0 here. So 1 times 0, we get this 0 here. 1 times 0, so you're going to move from the bottom to the right top, and then the 2nd value, and then the next value. So 1 times 0 gives you 0. 1 times 0 gives you 0. 1 times 1 is going to give you a 1. So that's why we get the 100 here. So that gives you a little bit of a more of a general idea, because anytime that you have a 1, right, multiplied by that top number, it's the same as that top number. So we have 100 here. And again, we would repeat 1 times 0 is going to give us the 0. 1 times 0 is going to give us a 0. 1 times 1 is going to give us a 1. Now, in the 2nd row, we wanted to move over 1 column, right? We shift it over 1 place, and then we do the adding. So the 0 here just drop down when we add those 2 rows together. The 0 plus a 0 is a 0. And remember your addition rule, right? We talked about that on Tuesday. So 0, technically it's a 0 down here. So 0 with the 0 is a 0. 0 plus a 0 is a 0. A 1 plus a 0 is a 1. And a 1 plus a 0 is a 1. So the final output for our multiplication problem in the example is 1100. Okay, so now what we're going to do is we're going to attempt A. Okay, so I'm going to go ahead and open my notes real quick. So we're gonna rewrite this. So I'm gonna handwrite it so that way it takes a little bit faster time just to get through this. So we get a 1 0 1 1 1 1 0. We're gonna multiply it by 1 1 0 0 0 1 0. So we're going to start it from the right-hand side. So just like what the rule has stated, 0 times 0, we get a 0, right? So technically, everything is 0. So 0 times 1 is 0. 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 0 times 0 is 0. 0 times 1 is 0. Then we move to the next digit here on the bottom and we multiply it across the top. So a 1 times a 0 is a 0. We shift it over one place. A 1 times a 1 is a 1. A 1 times a 1 is a 1. 1 times a 1 is a 1. 1 times a 1 is a 1. 1 times a 0 is a 0. 1 times a 1 is a 1. Okay. Then again, we are going to move to the next digit. So now we're going to shift left one more place for this 0 right here. So again, we would have, okay, 0 times a 0 is a 0. 0 times 1 is a 0. 0 times 1 is a 0. Again, 0 there. 0 times 1 is a 0. 0 times 0 is a 0. 0 times 1 is a 0. And you would continue to do that. Let me see if I can move this up more. For the next 0 and the next 0, right? So we took care of this 0, then you're going to do that next 0. So we would have 0, 0, 0, 0, 0, 0, and 0. And then once you write everything out, you're going to add them all up. Okay? And remember, when we talk about addition, we usually handle that 2 at a time. So you have to handle the top 2, take that output, add it to the next one. So we would do it by pair in each of the cases. Okay? So let me see if I might not have all the room here. Let me see if I can move down. So when you write everything out, these ones right here is going to give you the exact same digit. We're just going to shift left a little bit more. Once you have everything, you're going to add them up. Okay. Now, when you see these blanks, just think of them as 0 right there. So when you add it, so this 0 just drops straight down when you add. These 0 just drop straight down when you add. And then when you get to this column when you add, what's going to happen is you're going to add the top 2, get the output. So 0 plus 1 is going to give you a 1 in the middle there. And then 1 plus 0 again is going to give you 1. And that 1 is going to drop down. Okay. So when you add, make sure you handle the top 2 first, get the output, and then add it again to get the next one. And of course, we can check this plugging into the calculator, but manually, we need to know how to be able to do that. So at the end, you should have a binary value in specific length, right, as the output when you do the multiplication. Okay, any question with the technique? Okay. So as you work through A, then you can just type out the result out there. If you wanted to type out each step, that's fine, and show the multiplication for each of the digit and the addition. But if it gets a little bit too tedious, then you can just type out the answer there. That's fine with me. I want you to be able to know how to do this because on our quiz and our test, you need to know how to do manual calculation for arithmetic with binary. And then I'll start B. Let me see if I can write it smaller. And be able to walk you through most of the steps there. So B gives us 1, 1, 0, 0, 0, 1. Multiply it by 1, 1, 1, 0, 0, 0. So we'll start with the rightmost digit. So 0 times 1 is 0. 0 times 0 is 0. 0 times 0 is 0. 0 times 0 is 0. 0 times 1 is 0. Everything is 0 according to the rule. Again, we shift left one digit when we move over to the next one to do the multiplication here. 0 times 1 is 0. 0 times 0 is 0. 0 times 0 is 0. 0 times 0 here is 0. 0 times 1 is a 0. 0 times 1 is a 0. Then we go to the third 0. So again, we get the 0. 0 again. Everything should be 0. Then we get to this 1. 1 times 1 is a 1. 1 times 0 is a 0. 1 times 0 is a 0. 1 times 0 is a 0. 1 times 1 is a 1. And 1 times 1 is a 1. And then the next one, you should get the same as the top line, of course. So you just have to shift it over one digit to the left. So we would have 1, 0, 0, 0, 1, and 1. And then for the most left one on the second row, when we multiply it by the top, it's the same output as the top. We just have to shift it over one column, right? So we would have 1, 0, 0, 1, 1, and another 1. So you would operate the addition after you had multiply out each of the digit. This 0 just dropped down because technically all of these are 0 here. These zeros drop down. These 0 drop down. 0 plus 0 is a 0. 0 plus a 0 is a 0. 0 plus 1 is a 1. 0 plus 0 is a 0. 0 plus 0 is a 0. 0 plus 0 is a 0. 0 plus 1 is a 1. And again, these are going to give us 0. 0 plus 1 is going to give you a 1. And then these are all 0. This is going to give us 1 because 0 plus 1 is a 1. 1 plus a 0 is a 1. 1 plus a 0 is a 1. So you get a 1. Now this guy right here, this column is going to have carry. Okay, we talked about carry last time. So a 1 plus a 1 is a 0 with the carry. And then after you have that, right, you would have a 0 plus a 1 is a 1. Then you would take that carry and add it with the top one here. So a 1 with a 1 is a 0 again with the carry, and a 0 with a 1 is a 1. So you have another carry to the top left here. So this should give you a 0 and a 1 in the front. Sorry, I ran out of room there. Okay, any question? So this is B.
For the last one that you did the multiplication on, shouldn't there be an extra 0 if it's the same as the first two?
You're right. So this one, yeah, so a 1 and an extra 1. So when you do this, so this is a 1 and a 1 is a 0 with the carry 1. Thank you. And then this one is a 1, 1, 0, it's a 0. So a 1 and a 1 is a 0, 0 is 1, it's 1. Carry a 1. 1 and 1 is a 0 with the carry 1 and a drop down 1. Yes. So we would have to do the addition, and the easier one, as you can see, are the 0 that's going to bring down. But when we have a 0 with a 1, we would have a 1 as the output when we add. Okay. So the only one that's a little bit more challenging is when you have a 1 plus a 1, you would bring that carry 1 over. So that will be a 0 and then a 0. So you would handle 2 numbers at a time as you do the addition, and you would have the output. Okay.
Hi, Professor. Could you rewrite the answer, the final answer?
Yeah. So let me see if I can erase some of this and make it a little cleaner for you. So it's 1 0 1 0 1 0. Any question? Okay, so we have a little bit of practice with 1A in lab 1 doing multiplication. And same technique that would apply to decimal, but in binary, you only have 2 numbers to deal with. The only areas that we might run into issues is making sure that we add with the proper carry, right? And so when you have the 1 plus a 1, make sure you carry it over and then handle 2 number at a time. Okay, so some of this information is also in the notes for chapter 1, and that's on page 5. You see the same example here. I want to point this out as we kind of touched on this before on Tuesday. So we know that a byte is 8 bits in binary number, and it can have leading 0. So we talked about how sometimes the calculator would shrink it out and it would just disregard the 0, but usually if you can include the 0 in the front to represent the 8 bits. Then you have 256 different bytes that are represented for integers from 0 to 255. So when we have the digit 0 in the byte, we would have all 0 here, and then 255, we would have the all ones here. And some of this, if you're familiar with networking, you would see some of that because in the IP version 4, it uses decimal number to represent it in the octet. So for example, if you have like an address like 192.168.0.1, like for home use, then the conversion of that is the computer, when it sees that address, it's still going to convert it back to 0 and 1s, but it's going to handle the 32-bit of all 0 and 1s as the representation of the version 4 addresses. Now, when they transgression to version 6 address, IP version 6 uses hexadecimal, which we will get into next, okay? Also, I preview a little bit about Word. So in a Word, most of the legacy system, depending on the architecture, word size can be 16-bit, but more of the modern architecture, word size would be 32 or 64-bit. Now in Intel based, right, x86, you often see Word is represented as 16-bit. And you see some of this in assembly, classes when they talk about word size and what's consistent in a word. Later on, we will have some programming exercises where you're going to take a look at the value in ASCII for each of your character. That could be a letter, upper or lowercase, that's different, right? Or a symbol. And know that the lower 7 bits of a byte is going to be represented for ASCII. It's going to be 0 to 127 in equivalence to decimal. So once you hit the value of above 127, right, the computer won't be able to translate that as an ASCII equivalence, okay? And we'll see some exercises that pertain to that. For ISO Latin and Mac Roman, which is obsolete, that can go above 127. So when we deal with text with accent, like in different languages and such, you would see that some of the symbol that's used in accented would use special character that would reach above 127 in equivalence value for decimal. And you might be familiar with Unicode. And for all characters in all languages, and this is commonly used. This is used for web. This is used for our computing system. So it's mathematical and it's used for specialized character. And you would have UTF-32, also called CIS7, which is represented in 4 bytes or 32-bit. Now, we As I mentioned, we use hexadecimal for a lot of different things. And the common things that we normally see is, MAC addresses, right? If you find the MAC addresses, which is a physical address that is ingrained or programmed into your network interface card or your Wi-Fi. This address is given to the vendor who created your network interface card. So when you plug in your Ethernet cable to your Ethernet adapter, that adapter has a specific physical address that's using hexadecimal. Hexadecimal is also being used now for IP version 6 because that way we would have more of a combinations of addresses because it's base 16 versus decimal number, it's only base 10. So you have more variations with addresses. And yes, they're saying that we are running out of IP version 6 eventually, right? We will run out of it. And because we have so many devices, that's going to be utilizing, specific addresses, okay? And I'm talking about public IP. Then hexadecimal also being used in, if you ever do like HTML coding, right? You would use that for the color codes. So like a white, pink, blue, etc., that would represents with numbers and letters in hexadecimal system. So I created a little table so you can see. So when we have a number like 0 through 9, like if I have a 1, that's going to be equivalent to 1 in hexadecimal. So if 0 through 9 in decimal, that will be 0 through 9 in hexadecimal. And in binary, we would start with 0, 0, 0. Sorry, I'm missing a 0 there. It should be 4-bit. So 4-bit is going to represent 1 character in hexadecimal. Okay, so we would represent 1 character in hexadecimal with 4 bits in binary here. And when we reach to 9, it's going to be 1001. Then if we have a number in decimal as 10, hexadecimal is going to be A. And that's 1010. 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Okay, so now we see this table, we have a scale to work with, the comparison between different systems. Then, if we take a look at this example. So you have the A2, this is in hexadecimal because it has a subscript 16. This little 16 here tells us that it is a hexadecimal number. And we know that A equivalence in decimal is going to be 10, and 2 is 2. So what you do is you start with the right digit and you multiply it by 16 to the 0 power because it's the least significant. It's the least significant value to the most right. You would start out with the exponent 0 for the most right digit. Then you're going to add it to the next digit, which is A is 10 times 16 to the first. So in this case, we only have 2 hex digits. So this is going to be the calculation. We're only going to have 16 to the 0 times that rightmost digit plus 16 to the first times the next digit. Okay. So once we completed the multiplication and the addition, we should have 162 in decimal equivalents. So this is how we convert from hexadecimal to decimal. And if you take a look at the next example, because it has more digits, so as you move further to the left, the exponent is increasing. So we start with the most right, which is 2. We multiply it by 16 to the 0 power. and then the next digit we multiply it by 16 to the first, and then after that we would multiply it by the 16 to the second, and so forth. When we get to the last digit here, that will be 3. 3 is going to multiply it by 16 to the fifth. After you multiply everything out and add them together, you would have the decimal, which is the base 10 equivalence to that value. Okay, so now what we're going to do is we are going to take a look at the next exercise, number 2. So in number 2, it gives you 3 hex digit 21B base 16, and we need to convert it to decimal value. So what we do here is we write it out to 1B16. It's going to be equal to, and we would start out with the most right digit, which is B, and B is 11 in decimal. Remember the table. So we would have 11 times 16 to the 0. That's going to be B. So this is B. Then we're going to add it to the next digit, which is 1. So the next digit, which is 1, 1 is 1 in decimal. So we would take 1, multiply it by 16 to the first. And then we add it by 2 times 16. Sorry, let me erase this real quick to make it fit. Then we're going to take 2 times 16 to the second. So this represents B, this represents 1, and this represents 2. Okay? So we know that anything to the power of 0 is technically 1. So that's 11, because 11 times 1 is 11, plus 1 times 16 to the first, which is 16, plus 16 squared is 256, I believe. Let me double check.
Yes.
Okay, 256, and then multiply it by 2 should give you 512. So once you add all of this together, you should have the decimal equivalent. So if we take 512, oops, sorry, 512 plus 16 plus 11 is going to give us 539. Base 10. So 21B base 16 is going to give us 539 in decimal. Okay, and that's A. Any question regarding conversion? And this is the multiplication method for conversion from hexadecimal to decimal. Now, sometimes, right, some people, they would convert. It's easier probably for some people to convert it to binary and then to decimal, sure, you can do that as well. But this is one way. So as you have larger digits or more digits in the hexadecimal, you would have the multiplication to the 16 with the increasing exponent. Okay, so now what I can do is I can start the B with you, and then that way you can do the calculation. Any question on 2A in lab 1? So we need to know how to do this for our quiz and test.
On the quiz and test, will we be allowed to use a calculator, or do we have to do it all by hand?
I normally allow calculator any mode in quiz, but on the final exam, because lockdown browser, the way it's programmed, it's only allowing scientific mode for calculator.
Okay.
Yeah, like on the toolbar of the lockdown browser, it has a calculator button, and when you click it, it only gives you the scientific mode. So you probably won't be able to switch mode to the programmer because it has its own calculator, you know. So just to give you heads up that you might not be able to do that for the final, but on the quizzes, you're welcome to do that.
Okay. Thank you.
Yeah, no problem. Okay, so for B, we have A, 9, 3, and D, base 16. This is a little longer, so we want to write that out with the equivalents in decimal. And to recall, A is 10, right? And then you can use your table to match up. And your D is 13. Okay? So we would start out with D, which is the rightmost digit. So you would have 13 times 16 to the 0. I use parentheses so I don't jumble them up, and it's just better so that way you can multiply first and then add. And then 3 is 3, so 3 times 16 to the first, plus 9 is 9 in decimal, so 9 times 16 to the second, plus A is 10, so 10 times 16 to the third. Okay, so we know that this is 1 right here because it's 0 power, so you would have plus 13 back here. And then 3 times 16 should give you 48, plus, and then this is 256 times 9. So let me get my calculator here. Is 2304. Plus, and then the next one is 16 to the third times 10. So let me get to scientific. So 4096 times 10, which is 40960. Then you add this up and you should get your decimal equivalents. Okay. Sorry about my chicken scratch. I now type everything, so I'm not that good in just writing on screen. Any question? So that will be 2B. This is 2B in lab. Okay. So we spent a little bit of time to go from hexadecimal to decimal. Now we got to go in reverse. Okay. So as we use the multiplication method to go from hex to decimal, when we go in reverse, we would do the division method. So I'm going to go to notes real quick and give you a little bit more on the instruction. Now, right before we do the other conversion, I want you to look at this real quick and make notes of it. It says each hex digit corresponds with 4 bits, which is half of a byte in nibble. So whenever you write out the hexadecimal, you would know that the D here would represent 4 bits in binary. Okay, so let's say that we want to really make this into the binary. Sure, you can take the decimal and then start doing the subtraction, but the easier way to convert this value to binary is looking at each of these as 4 bits. So let's start with the right hand side real quick. So now we're gonna make this into binary. Okay. So the D, we know that D is 13. How can we represent 13 in 4 bits? Okay, so we know that the first bit would be on for 1, right? And then 2 is going to skip, and then 1, 1. So this is 13. Okay, because 4 plus 8 is 12 plus 1 is 13. Okay, which is D. Now the next one, we move over to the left one digit. So we have a 3. So we know that the 1 and the 2 is on and the 4 and the 8 is off. This is 3. Then we move over to the next one, which is 9. So you know that the 1 and the 8 is on. So 1, off 2, off 4, and on 8. So this is 9. And then A is 10. That's super simple. That means it's 2 and 8. So we would have the first one off, the second one on, off, and on. This is going to give you 10 or A. So technically, this right here is this entire binary value. It's a lot simpler to really convert it to binary versus, you know, going into decimal, because decimal then you would multiply and add. So this is why they say that each character, each digit in hexadecimal is going to be 4 bits in binary. So any question? Okay. So now we're going to go in reverse. We're going to go from hex to decimal by doing the division. I'm going to go ahead and erase this, okay? So in the division method, we care about the remainder. And since it's base 16, we're going to divide it by 16. Just like how we use the division method to divide it by 2 for binary. So in here, it says that first you're going to take the decimal value and you're going to divide it by 16. You would have a quotient, and whatever the remainder, you would want to make a note of that remainder, which is going to give you the value in hexadecimal. So think about this in programming's perspective, right? That's a mod, right? Because when we deal with mod, we actually take a look at the remainder, okay? So as we do that, we're going to repeat it until the quotient becomes 0. So if you have anything else in the quotient, you're going to have to keep on going until it gets to 0. Okay? So in this example, you have 7,562 in decimal, and you want to make it into a hexadecimal. So you start out, the first step is to take this value divided by 16. When you divide it by 16, your quotient is 472, but you should have a remainder of 10. And that remainder 10 tells us that 10 is A. Since we still have quotient that is not 0, we have to continue to divide it again. So 472 divided by 16 gives you 29 as quotient with the remainder of 8. 8 is 8 in hexadecimal, so we record the 8. Okay, and then 29 divided by 16 is good, because 29 was the quotient here, it's going to give you 1 with the remainder 13, and 13 represents D. And then 1 is still of significant in the quotient, so we take 1 divided by 16 gives us a 0, right, with the 1 remainder, so that's going to give you 1. So the way we write this out is the A, the first one, is going to be on the right. Okay? And then the next digit is 8. And then the next digit is D. And the next digit is 1. So the first remainder, that's going to be on your most right when you go through the division. Okay? So let's do the next question together, number 3. You wanted to take 801 in decimal and you divide it by 16. So I'm going to start a little bit on the bottom here, so that way I have room to work toward the top. So I have 801, oops. And I'm going to go ahead and divide it by 16. And this is when you're going to use your long division technique. Okay, so if we just taking a look at the 80 right here, 80 divided by 16 is 5 times, right? That's going to give us 80. That subtracts evenly, right? And then we're going to bring the down here, the 1 down here. So that's 1 divided by 16. It's going to give us the 0. So we have a remainder of 1. Correct?
Yes.
So you want to record this. So normally I put a little R just to keep track, because after a while we lose track of it. Okay, so we have a quotient of 50. We're going to divide it by 16 again. So let me, sorry, I'm going to make it a little cleaner so you follow. So 50 divided by 16. Okay, so that's 3 times. That gives us 48, which gives us the remainder of 2. Okay. So we have a 3 here. So 3 is still of significance. So 3 divided by 16. Of course, it's 0 time, right? Because it's smaller than 16. So technically you have an R. Oops. You have an R3. So the first division is going to be your least significant value. That's still going to be the most right. And then the next is going to be the next digit to the left of it. And then the next digit is going to be to the left of it. So the way we write this out is 3, 2, 1. Okay. Any question? So if you haven't done long division since grade school, then now it's time to dust that memory and be able to do that. Okay. Now you can convert it back to see if it's equivalent. So any question with 3? Okay. So when people program the calculator like this, right, think about how you would program something like a program to convert. You see a bunch of them online, or you can download a calculator. So we can say that we would apply mod, right? And to get our calculator to convert for us. Okay, so for 4, I kind of previewed this a little bit earlier already, so I'm gonna work with you on this. So is it okay if I erase this, or anybody still taking notes? Okay. So in 4, we're gonna take that hexadecimal value and we would convert it into binary. And you know, you saw some of this like right before we show the division method. So you would have the B61 and we get the hex, and we wanted to make this into binary. So you start out with 4 digits each of the hex value here. So a 1 is a 1, so that's easy. 0, 0, 0, 1. So this is a 1. And then a 6 consists of a 2 plus a 4. So 1 is off, 2 is on, 4 is on, and 8 is off. This is going to give us a 6. And then B is 11. So that means that 1 is on, 2 is on, 8 is on. So we have 1 on, 2 on, 4 off, and 8 is on. That gives us 11, which is B. So what's your answer? 1 0 1 1 0 1 1 0 0 0 0 1. A lot quicker than, as you can see now, right, at the machine level. I think, you know, binary, once you get a hang of it, it's just super easy. So the way the computer see this hex value, it's going to interpret it. It's going to say, oh, this is the binary equivalence. Any question with 4? And if you don't want to ask now, I reserve some time at the end for you to address any questions that we need to answer. Okay, so this is number 4. And you can try 5, right? 5 has 4 characters, so you have 95C2. So we would start with the 2. 2 is 2. So you would have 0 0 1 0. So I'll help you with working that out. Give you some practice. So 9 5 C2 to this is a hex. So a 2 is a 2. So we know that one is off, 2 is on, and 4 and 8 is off. So this is going to give you a 2. And C is 12. So we know that 4 and 8 is on. So 1 off, 2 off, 4 and 8 is on. That's going to give you 12, which is C. 5 consists of 4 and 1. So 1 on, 2 off, 4 on, and 8 off. So this is 5. And then 9 is easy, 1 and 8. So 1 on, 2 off. Sorry, let me move this over a little bit. 1 on, 2 off, 4 off, and 8 is on. This is going to give you 9. So our answer for this is any question? Okay, so super simple. Once you get a hang of the conversion from decimal to binary, you can do a lot with the other number system as well. So your notes contain example. It shows you how you can also look at multiplying it out, doing the division. Let's talk about octal system. So similar to hexadecimal, but on a smaller scale. So octal was common for the legacy computers back in the day, because when we started out with computing, when computer systems started to be more popular and the design and with the architecture, we started out with 8-bit, 16-bit based systems, and then we transitioned to larger bit size architecture like x86, which is 32-bit, and now we're currently at 64-bit. Okay, so what you see is we would use the same technique to be able to do the conversion. So you would start out with the right digit. When you're going from octal to decimal, you would start out with the 3 here, and you would multiply it by 8, therefore the term octal. So 3 times 8 to the 0 power for the rightmost digit, and then 2 times 8 to the first, and 7 times 8 to the second, because this one only has 3 digits. So when we multiply that out and do the addition, we would get the decimal equivalents. And in this one, it has more digits, so we would continue to increase the exponent as we move to the left from right to left. Okay. So the same technique that's applied to hexadecimal conversion, right? From hexadecimal to decimal, we would use the same technique to go from octal to decimal. Now, I want to touch on the binary aspect, because it's a lot easier for octal because it's such a smaller system. So it's better if we just take a look at how octal is represented as binary. So instead of 4 bits like in hexadecimal, we would represent it as 3 bits per digit. So as you can see here, these right here represents the 3 because it's 1 and 2. That's gonna be the 3. And then 2 is represented as 0, 1, 0. So in binary, this 2, 3 in octal is represented as this binary value. So you just break each of the digit in octal into 3 bits. Instead of 4 in hexadecimal, we use 3 bits in octal. Okay? So let me see. So we're going to do an exercise before we get into 2's complement. Okay. Two, 4, 10. Now, when we go in reverse for this, what you can do is you can do the division method, like what we talked about. But let me see. 124. So you can use the division method to go from decimal to octal, or what you can do is you can convert the decimal to binary and then to octal. So there are 2 approaches in this. We can take 124 and divide it by 8 and divide it by 8 until we can't anymore, which is the division method. Or we can, so I'm going to do one that's going to be the division method, and then I'm going to do another one in binary conversion so you can see. Okay. So let's start with the first one with the division method. So we have 124, and we're going to divide it by 8. So 12 goes into 8 one time with the 44 down here. And 44 goes to 8 5 times with the 4 remainder. Okay. Then we have a quotient of 15, so we need to continue to do that. So 15 divided by 8, that's going to be 1 time with the 7 remainder. And then we still have a 1 as a quotient. We have to keep going until it's a 0. So 1 divided by 8 is going to give you a 0 time with the 1 remainder. Okay. Now your calculator also have the octal mode. Sorry. Okay. So if you have, let's check. Oops. 124 in decimal, and we wanted to get into octal, it's 174. Now, in hexadecimal, the first one is going to represent the most right character. So this one is the same. So it's 174. 174 octal. So the first one is your LSB, your least significant bit. Okay, same technique as your hexadecimal. So any question regarding division method for octal? You just simply divide it by 8 until you get to the quotient 0. Every time you get a remainder, record it, because that's going to represent your octal value. Okay, so this is 6A. Next, I'm going to do 6B with the binary conversion then to octal. Can I erase this? Everybody okay with this? And again, I'm going to upload the Zoom recording. If you're interested in rewatching it, the caption one, I will push it through YouTube so it caption it for me, and then I will link it. It normally takes a couple of hours to send such a big file. Anything above an hour is huge, and then it's going to do the caption. So when we do the 6B, let's go from decimal to binary and then from binary to octal. Okay, so here is 62. So 62, 10. So when we converted the binary, we would say 1, 2, 4, 8, 16, 32, 64, right? We don't need to go further than that because we only need 62. So I'm going to use the subtraction method. So 62 minus 32 is going to give me 30. So I subtract that one. 30 subtract 16 is gives me 14. And then 14 is going to be 8, 4, and 2, right? 14 subtract 8 is going to give me 6. 6 subtract 4 is going to give me 2. And 2 subtract 2 is going to give me 0. So what we need to do is we need to chunk it into 3 bits each time. Okay, now let's look at the representation from the calculator. So if we have the decimal, 62 in decimal, our octal is 76. Okay, do you see 76 here? But you cannot look at this number now. Okay, I want to erase this so it doesn't, okay. So this is our binary after we convert from decimal to binary. Then what you're going to do is you're going to chunk it into 3 pieces, and it's only going to go up to 6. That's what that piece of notes is talking about when it's discussing octal. So you're going to put 1, 2, 4. 1, 2, 4. And then the 0 is just 0, 0 in the front there. So we can disregard the 0 there. So if you add these together, you get a 6 here, right? A 4 with the 2. And then if you add these together, because all 3 bits are on, you get a 7. And that's how we have 76 octal. Okay, any question?
Professor,
Mm-hmm.
how do we get the 111110 from the 62?
So let's go back. Remember, were you attending the Zoom on Tuesday?
Yes.
Okay. So we talked about how I have you use that table, right? Because it's multiple of 2. So let's say that we have that table, right? And we would start our table, have 1, 2, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, and this can go on more, right? I stop here is because I only need up to 62, and I talk about subtraction method. So which number on this decimal equivalent value, right? Because this is 2 to the 0, 2 to the first, and 2 to the second, and so forth, right? right?
Yes.
Which number I can subtract on this line right here from 62?
32.
32, so that's on, right? So if I subtracted 62 minus 30, sorry, 62 minus 32, I get a 30 left, right? So I still have to subtract more. So I can subtract the next number, which is 16. So 30 minus 16, I get a 14, right?
Yeah.
Then I subtract the next number, I get 14 minus 8, which gives me what? 6, right?
Yeah.
Next number I subtract 4, which gives me 2. Subtract it again, 2 minus 2 is 0. So we start out with simply converting it to the binary. So we're going to go from decimal to binary, right? Okay. So once we have the binary, the next step is to break that binary into 3 bits. Okay. So after you have the binary, you would forget about all of this now, right? You just need to use that to get to the binary. Okay.
Okay.
Now what we're going to do is we're going to chunk it into 3 bits. Okay.
Okay.
So at this point, we're going to, let me get it into a different color. Okay. So now in octal, it's only going to go up to 6 decimal equivalents because there's only 3 bits in the octal system, right? It's up to 8. So when you chunk it into 3 each time, you would start with the most right. The decimal equivalent is 1, 2, and 4. Okay. And then again, another 3 bits. Forget about everything else. And another 3 bits. It's 1, 2, and 4. It's never going to go higher than 4 equivalents in decimal for octal. Okay. So first we convert decimal to binary. Then what we need to do is we need to find the equivalents that's represented in octal. So in octal, it's only going to be 3 bits per digit. Okay. So we're going to start with the right. We're going to break it up into chunks of 3 bits. Then any bits that's on, you're going to add it. So we're going to have 4 plus 2 is going to give me 6. That's one of, this is the first. Sorry. It's that one. Okay. Then we're going to take care of the next 3 bits. So 1 plus 2 plus 4 is going to give me 7. So we have 7 here and a 6 here. So that means it's 76 octal. Now you can do the division method. You still get the same thing, or you can do the 2-step conversion. So you go from decimal to binary and binary to octal. And when you go from binary to octal, you break it up into 3 bits a piece. Any bits that's on, you're going to add it, and that's what you're going to get. Okay, and it's never going to go higher than 4 because there's only 3 bits for the octal value. Okay.
Thank you.
Yeah, no problem. I know it's a little confusing because you're like, oh, you just show us that it goes higher than this, but That's for the binary conversion piece. And then for the octal, because we only care about 3 bits at a time. So you're going to stop at 4.
Yeah, I was confused about this too. Thank you.
Yeah, no problem. Now, a lot of people prefer this method because you don't have to remember higher number or doing the division and remember the remainder. So either way, like whichever works for you, of course you can use a calculator and crank it out, but I want to show you 2 methods so you know how to approach it, right? If you have to really illustrate on how to do this, right? And technically, anything that we can go through the process, we can program. So if you create a program that's writing this out, then you have to convert it into 2 steps. So you write the function in order to do the conversion, convert it to binary, convert it to octal. Okay. All right. So you got a little bit of 6A in division and then 6B in binary octal conversion. Okay, so now I have about 43 minutes to address 7, and then I hope to get it done before that. All right, so let's talk about 2's complement. 2's complement is important because 2's complement really represents negative value in human world, right? In the computer world, the negative value is a sign value is 2's complement, because we have to tell the computer how to interpret that negative sign, and the computer only understands 0 and 1, so we have to find a technique to really let it know that this is a negative value. Okay, so this asks you to find the 2 complement of 89. So in our world, we say, oh, if it's a positive 89, then the negative value of it is negative 89. When you punch that into your calculator, the negative sign with an 89, the computer has to interpret that and say this is the binary equivalence. So when you see a decimal like this, what you would do is you would start out with first converting it to binary. Okay, so the first step is to take that value and convert it into binary. So we can use the subtraction method that we've been using, or if you like the division method, that's fine, as long as you get it into the binary value. Okay, so we have 1, 2, 4, 8, 16, 32, 64, and 128. I don't really care about 128 because it's 89 is less, right? So 89 subtract 64 is going to give me 25. I skipped 32 because that's too large. 25 minus 16. That's going to give me 9. And 9 is going to subtract 8. It's going to give me 1. And then we're going to skip 4 and 2. And 1 subtract 1 is going to give me 0. Okay, so that's here's the binary equivalence. So are we following so far? Any question with that? So I simply use the subtraction method, and I go down, pick the number that I can subtract 89 with. If I subtract it, I put a 1 on top, and I skip the number that I couldn't subtract with the remainder after I do the subtraction. So when we get through the end, we should have the binary value. Okay. All right. So no question with that. We got that. Now, since you have the binary value, the next step, step number 2, is to flip the bit. So in programming, we would say 89 decimal, and then the computer is going to say, oh, this is the binary. Then in the back, we're going to NOT it. So when you not something, it's the opposite bit. So if we flip the bit or not it, the 1 becomes the 0 and the 0 becomes the 1. So when you apply the logical gate not, it's going to flip the signal. So when it's on, it's going to switch it off. And when it's off, it's going to switch it on digitally. Okay, so here is our binary value. And so it's 1, sorry, it's 1 0 1 1 0 0 1. That's our result from 89 decimal. Then when you not this, or flip the bit, I call it, a lot of textbooks call it that way too, you're gonna get 0 because the first bit is on, so it's gonna switch that off, and the 0 is gonna become the 1. So when it's off, it's gonna turn it on. Then the 1 becomes the 0, and the 1 becomes the 0, and the 0 becomes the 1, 0 becomes the 1, and the 1 becomes the 0. This is what we call the first complement. So in any number, you have to make it, you have to convert it into binary to start. Once you convert it into the binary, then you're gonna not that binary value, you're gonna flip the bit. Then after you flip the bit, you're gonna add the 1 to the flipped bit, to the not output. And that's gonna give us the 2's complement. There's 2 steps, right? So after this, I'm gonna take this, I'm gonna plus 1 to it. So we're gonna have 0 1 0 0 1 1 0 plus 1. And it's technically, if you add a 1 here, it's just gonna be, the front is gonna be the same because there's no carry, because there's 0 in the back. So it's gonna be 0 1 0 0 1 1 1. It's just gonna add that 1 to the 0 bit here. And this becomes our 2's complement. Okay? So how can we check this, right? If you wanted to check the output, put -89 as decimal and then look at the value in binary.
Is that kind of like an inverse?
Inverse is just not. Yeah, well, if you say inverse in the sense of change opposite, because inverse is really the opposite, right? Then it's just not. That's the first complement. The 2's complement would be after you not it, you're gonna add the 1 plus 1.
Okay.
Yeah. So, and students tend to forget that step. So when you get to Cal State San Bernardino, Cal Poly Pomona, UCR, when you take the architecture class, some professor, right off the bat, they expect you to know how to do 2's complement, because when you're handling stuff with processor, right, a lot when at the low level language, sometimes when you have to write instructions for the process to operate, and you have to understand that what is a 2's complement of something. It just represent a sign value of it. Okay, and everything breaks down to be number, because ultimately we bring everything out to be binary. The computer understands a binary and signal, right, on and off digitally, digital circuits. So we have to represent it somehow, so that way our human number would be understood by the computer and utilize it to process, whether it's information, mathematics, whatever it is, right? So this is how we represent a sign value. So this is 89. This is -89. Okay. So when I say to find the 2's complement of 89, I'm literally asking find the binary equivalence of negative 89.
And if you add those two binaries, you should get 0, correct?
Yeah, just like how you take 89 minus 89. Yeah,
Okay.
mathematically it should cancel or get back to 0. Yep. Okay, so let's try B. Right, I have 30 minutes, so I wanted to hit B and C all together. C and D is super easy because I already gave you the binary, so you not it and then you add the 1. I try not to use the flip the bits a little bit because sometimes students get confused about that. And then we'll get into logical gates next week, you know, to do the truth table. Okay, can I erase this now, or is anybody still looking at it? Okay, so let's try B. So in B, same thing. So you start out with 161 and then you would convert it into binary. And then from binary, you would not it and then you would add the 1. So we have 161 and that's decimal. And then so we have 1, 2, 4, 8, 16, 32, 64, 128. And I don't go to 256 because that's higher. So we start with 161 minus 128. So you subtract it, put it there. So that gives me 3, 3. Right, 33. I skip 64. 33 minus 32 gives me 1. Skip this, 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 and this, and 1 minus 1 is 0. So here's your binary value. 1 0 1 0 0 0 0 1. And that is the positive, right? It's equivalent to 161 right now. But we want to find the 2's complement of that. So the next step is to not it. So the first 1 becomes a 0. The next 0 becomes a 1. The next 1 becomes a 0. The next 0 becomes a 1. The next 0 becomes a 1. Next 0 becomes a 1. Next 0 becomes a 1. And the last 1 becomes a 0. And this gives us the first complement. Is when we not the 161 binary equivalence. We don't complete until we add the 1 to this. So we're going to take this and we're going to do a plus 1. So 0, 1, 0, 1, 1, 1, 1, 0, plus 1. And simply, this is a 0 and a 1, so you just get 1 there. Nothing carries, so drop everybody down. 1, 2, 3, 4, 0, 1, 0. And this is your output, 2's complement. Okay? So in any case, we wanted to get it to binary. Then from binary, we're going to not the binary. So we're going to flip the bits. That's going to be the first complement or 1's complement, first complement. Then we want to add the 1 to get you to the 2's complement. And C, I already give you the binary, so you simply start with not it and then add the 1. And if it carries, you gotta make sure you carry it to make it right, to get the right answer. Okay? Any question? I'll start C for you, and then I'll leave you to do D, and that would wrap up. I don't think I have anything else for you after that. So, all right. Any question with 7B? This is 7B. Now, I know at Cal State San Bernardino, if you take classes with some of the professor, they make you write out the steps to show first and two's complement, or their equivalents of assembly, the architecture class. That is where you start as well. And then if you take, like, if you're in engineering at Cal Poly Pomona, get into digital circuits, you have to also know the basis of this, because binary arithmetic comes back to the basic level. So, all right, C. So we have 1 0 0 1 1 and 3 0 in the back. First, we're gonna knot it. So if we simply flip the bit, 1 becomes 0, 0 becomes 1, 0 becomes 1, 1 becomes 0, 1 becomes 0, and the 3 0 in the back becomes 1. And this is the first. Then the second complement, you're going to take this, and then you're going to do a +1. So 1 plus 1 is a 0 with the 1 carry, 1 plus 1, because this is technically 0 right here, right? All of these are 0, so just think of it, they're all 0. If it's easier for you, you can fill it in with the 0. So a 1 with a 1 is a 0 with a carry, and then a 0 with a 0 is a 0. A 1 plus a 1 is a 0 with a carry, and then a 0 with a 0 is a 0. And then a 1 with a 0 is a 1, and a 1 with a 0 is a 1. And then we're done with the carry, so that will be 0. 1 with the 0 is a 1. 1 with the 0 is a 1, and that's just a 0. So there you go. Do you have questions for me?
So are we, for the first complement, we
Mhm.
basically, when we're adding the 1, we have to add all those zeros towards the left as well?
Yeah, so if you have the carry, make sure that you apply the carry accordingly.
Okay.
I put the 0 because it's I'm a very visual person, mathematically, computing, whatever. When I learn, like, I wanted to see it, so I put the 0 there. It helps me. And so I recommend it because, that way, you would do 2 level, right? Because 1 with a 1 is a 0 here, and then a 0 with a 0, I get a 0. So I see it. Yeah, the little middle number, when you have a carry, you handle 2 number on top at a time. The carry with the top, and then the middle with the bottom. Just like how we did on Tuesday. So yeah. Now, if the last 2 that we did, it's nice because the last digit is a 0. When you add a 1, it just adds that 1 to the last part. So it's very clean. But in this one, you have a bunch of carries, so you gotta make sure that you operate the carry.
Okay.
Mm-hmm. Okay. So D, you have to complete because Dr. Wynn cannot give you all the answers. I can, but you should practice. That's you know, you apply your knowledge. That's important. Okay. So make sure we know how to do two's complement for our exam quiz, and also use it for your, future classes. This is important. I drove my both classes, CIS7 and 11. It's very important in assembly. So when you take assembly, it's better if you understand how binary works, and so you can visualize it and you can check it. I teach LC3, and then I did teach x86 with Microsoft ASM before. It's harder than LC3 actually. But I know NSM and ASM, maybe in the next one, I don't know, I might try ARM to teach ARM to the students, but it's pretty close to LC3. So. Okay, any other questions? All right, type in the chat your full name. I'll still pull the participants report anyways, but just in case they ask, right? You're actually presently there on Zoom. Type in your name if you haven't done that. I'm gonna reserve like a little bit of time left now for specific questions. If you need me to review certain ones that we went over, if you're not clear on something, you can stay on and you can ask questions. If you complete everything today, please submit it on Canvas. This is a larger class. I will try to do a week turnaround as far as grading, and then I'll get into the rhythm and I will try to get that. Sometimes there's a little bit of delay, and I will let you know because I might have like other things coming at me for projects and different things in the department, but I will try to get it. So next week I will try to clean up the grade for this week, just to give everybody a chance to get things submitted by the due date. I think I open it until tomorrow for due. So if you don't finish it tonight, spend a little bit of time and get it done before the weekend so you can enjoy the weekend. And then I'll see you here on Zoom again on Tuesday. If you have any questions or any concern between then, just send me a message. Okay. All right. If you want to stay on and ask questions, you can. If not, have a wonderful night. We finish a little bit early, but next week we'll do different things. Okay. All right. Thank you.
I had a question, Professor.
Sure.
On the binary number, I kind of assumed that the leading one made the number negative. Is there some gray area there? It just depends on how many bits you're using, I guess.
Yes. Yes,
Okay.
that is correct. So when you're looking at the calculator, especially I'm using a Windows calculator, this is going to tell you the bit size right here, right? This is going to give us 64-bit because even when we're using 64-bit architecture now with the processor, Microsoft still use word size is 16, and because that way it will work with the legacy 32-bit, which is x86. So your applications, the way they build the exe is based on the legacy. You want to make sure things are compatible when you upgrade. So this is the 64-bit, and then when you change your bit size down to the word or the byte, yeah, it starts shrinking down and it's going to remove the ones in the front. So if we go back to 7A, right? Let's say that I start with the Q word, right? If I do 89, a negative 89, you see how it fills in the rest of them and ones in the front right here. But if you shrink it down to 32-bit, it reduces it down to what it shows you in that was stored in that allocation for 32-bit. And then when we shrink it down again, right? And then eventually, right, this is a byte, which is 8 bits. So yes, it can be, confusing when you don't have all those ones in the front, especially when you're looking at binary. But the sign number should always have all of the ones in the front. And those ones in hexadecimals are Fs. Okay.
Okay, so all the leading ones turn into ones, I get. Because
Yes.
in the book it was saying it was the leftmost one would be a 1.
Yes. Assuming that if
Okay.
you're looking at the current byte size, Dr.
Oh,
Phelps, she
okay.
refers to the byte size. Yeah, the most significant would be a 1. But then
Okay.
if you're looking at the most significant for 64-bit, it's the most left one. So all of those ones fill in. And when you see this, right? If you look at the hexadecimal, see, that's all Fs in the front, because you remember when we're
Okay.
looking at 4 bits each time, those are Fs.
Yes. Okay.
Yeah.
Thank you.
You're welcome. Any other questions?
I have a question.
Yes.
When it comes to the homework and the assignments, do you want us to provide you with a copy of the work, or do you just want me to provide you with the answers on the sheet, the work document?
I'm fine with, if you wanted to submit just, question and answer, I prefer to have the question and the answer together when I check it, even though I wrote the assignments, because, going through like 40 students, sometimes I glance at it, I look at the answer and the questions. But, and some students, they handwrite all their solutions out and they scan it. I'm fine with that too. So either way, if you keep it all together, if you scribble on top of the document as you solve it and you save it like that, that helps you, then you can chart it in like that. Okay, I'm fine with it, with handwritten. But if you want to type it up and keep it clean, sure. I'm not picky with that. This stuff is really for you.
Right.
Okay. All of this thing, right? Like, my explanation, because I have to assess you to see if you understand or not. All of this is for you. And so, yeah, anything, if I can read it, as long as it's legible, it's fine. That should answer the question.
Okay, thank you.
Uh-huh.
I have a question
Yes.
about the when I log my assignment. Where you want me to put the name on the file or in the document?
Say it again. I prefer it in a document format. So if you scan it, it's a PDF. I'm okay with that. Some student, they submit it like a JPEG, like they use their smartphone to take a picture. If you don't have a scanner at home, I'm okay with that too. But if you're using a tablet, a lot of the time when you save it, you have an option to convert it. You guys know that you have free license with Adobe through the school, so you can always use Adobe to edit and convert. But anyway, if you absolutely have no ways to convert it to PDF, then yeah, you can send a JPEG with it. JPEG is kind of limited because sometimes, I can't, it's hard to see some of the stuff when the picture is cut off or something like that. But I don't know if I answered. Yeah. So if you can't scan it, or if you can't save it as a .docx or a .pdf, I'll take otherwise, but I prefer a document format.
Okay, and for the name, why do you want to put the name in the file?
Repeat your question again. It was a little echoey.
Oh, okay. I asking about the name. When I have to put my name in the document.
Oh no, yeah, because our grade book is great on Canvas. When you submit it, it links directly to your name to the grade book, so I don't have to worry. Yeah, so when you submit it, it gives me individual links, and then as I go through the grade book, yeah, it will shows what you submit when, so there's no way that I can mess up unless I manually go back and edit things. But Yeah, usually it gives me a link. So no, you don't have to put your name. You don't have to put page cover. Some professor require that. But if you like, you can. I don't require it.
Oh, okay. Thank you.
Mhm.
I had a question about 7C that you did on the last one.
Yes.
Why at the end did you not bring down the 0?
Why did I not bring down the 0 here?
Mm-hmm.
Because I added the 1 for the second the 2's complement. So when we started with C, this is the given to us right here. Okay. So we started with this value already, right? Then we have to knot it. So when you knot it, you basically flip the 0 into 1 here. Okay. So that will be your first complement. So when you have to flip it, you have to flip the bit or knot it to get it here. Then you're going to add the 1. So technically, I just add the 1, which is 0, 0, 0, 1, for the 2's complement rule. So the 2's complement is take that binary value, flip the bits, and then the second complement is to add the 1. So when I add the 1, 1 plus 1 is 0 with the carry. So this is why it's a 0 here. Okay, and then I continue to operate the carry. 1 plus 1 is a 0 with the carry. 0 plus a 0 is a 0. 1 plus 1 is a 0 with the carry. 0 plus a 0 is a 0. 1 plus 0 is a 1. 1 plus 0 is a 1. And then 0 plus 0 is a 0. 1 plus 0 is 1. 1 plus 0 is a 1. And 0 plus 0 is a 0. Okay, so at the second complement, after you flip it, you have to add the 1. Otherwise, it won't be 2's complement. So when we add the 1, we get a 0 at the end.
Okay, thank you.
Yep, you're welcome. Other questions?
I do have a question, but it doesn't pertain to the worksheet.
Okay, no problem.
Last Zoom meeting, which was on Tuesday, you did mention stuff about internships. So I'm curious to learn more.
Okay, yeah, so I'll put in the link. I have a grant through the Department of Defense called Cascade. This grant is gonna run, they just extended until this no, June of next year, because we were supposed to close it out in December. And through the grant, they have these smaller companies that are contracted or awarded money from the DoD. They picked the interns from our intern pool. So what we do is we put up an application, and the students that are going through the internship would have to fulfill requirements to assist the company with different processes in cybersecurity. I have a mixed bag of company. Many of them look at computer science students, not just cybersecurity students. So I have 2 students right now that are part of the computer science group, and they are doing hardware and software testing for one of the company that produce camera system for the military. So it requires, but you have to have also some cybersecurity knowledge, like some networking and stuff like that. So I will put up the application. If you like, you can apply for it. And then you have to go through background check. After the background check, we actually send your resume to the receiving company, and then out of that they select. We pre-select, and then after we approve the application, we send it to the company and then they pick. And the maximum that they can accept is 3 per companies. So, and you know, the process is a little lengthy because there's government processes involved, and then there's foundation money, but the pay is about $15, not that much, but you have great experience with it. And then you are required to fulfill a certain amount of hours. So if it's 2 students, you can go like above 85. And then if it's 3 students, then it's only 75 hours per, and you can spread it out throughout the semester. And then I have an apprenticeship program that's coming up. I'll have the form for you guys to fill out for that as well. It's through work experience course, and we have companies that will pay the students to kind of like shadow and learn in the process, and eventually be hired by them. So it's a little bit different than the internship program, and you have to sign up for the course. So either you get the credit or you get paid. And if you choose to get paid, right, there's a limit on, it's like a length of the semester, and then you can go to the next track to continue the same work process. But the whole point is to get you some experience while you are here in school. And we have quite a few companies. They told me that they're looking for C++, Python, Java, and web development. One organization in particular is the Water District. They are looking to replace some of their developer that's on the way to retirement. So those developers, they want to train, or system engineer, they want to train some of the students to basically kind of take over eventually. So they have like a year before retirement. So that's what they're saying. So I will let you know further. I just dropped an email to the director of apprenticeship, and she's supposed to put together some package for me. And once I have that, I'll put it in Canvas and you can apply for it. Okay?
Okay. Thank you.
You're welcome. Other questions?
Professor,
Mm-hmm.
for when we're converting the decimal value to a hexadecimal, we should always be dividing by 16, correct?
Yes, that's the division method that I showed. Yeah, for the 801 here. Yeah, so you always should divide, and then the remainder, remember that it's of significance. So let's say I'll do another example for you. So we don't have to do a large number. So let's say that I have 214, right? And I wanted to make it into a hexadecimal. So what we can do is we can start with 214 divided by 16. So 21 to 16 is 1 time with the, so that's going to be 5 difference, and then 54 to 16 is 3 times. You see, yeah, that's 48. So that's going to give you 6. Or maybe I'm off 4 times. Okay, so 54, right? No, maybe I was right. See, I'm rusty now. Okay, 3 times 54, 6. Okay, yeah, I was right the first time. 3 times. So here's 48. That's 6. Number 1, 2. Yeah, so you have 6 remainder, R6. Okay.
Okay.
Then you take 13, even though it's less than 16, that will be a quotient. So 13 divided by 16. So literally we should have a 0. Oh, I'm sorry, a 1, right? I'm sorry, a 0 with the 13 remainder. Okay. So 6 and then 13 is a letter. Yeah. So as you go through, you just keep dividing until you get a 0 as a quotient.
Okay.
Yeah. And then you can check, use your calculator to make sure you check, because as you get a larger number, it's going to be harder.
Uh-huh.
Any other questions?
I got a question, Professor. I went ahead and added the 89 and its 2's complement, and I got a leading 1 in the front. Do I just ignore that one?
Yes.
Okay. It
Because
kind of just comes off.
that one thing, think of that one as a negative sign for us.
Oh, okay.
Yeah. So when you do the, so because when you do the 89 negative, right, we mentioned that these ones right here, because it just carried a 1, these ones
Yeah.
right here just represents the negative sign for human. So
Okay.
so yeah, that would be a sign value, we say. And then
Yeah.
in hex it's F.
Okay. Thank you.
You're welcome. Other questions? No other questions? Braxton, sorry, I saw your email coming through, but I was in the middle of the lecture, so I couldn't. Yeah, but I'm glad you could join. But I will check my email after class. And Melissa, I wrote you about Python. They mentioned that you need to talk to your counselor, and then in the case where if you want to challenge the class, they can give you the final exam, and then the professor will grade it, and they will give you the actual exam, and you can test it. But in the case you don't want that, then I know RCC runs the Python non-credit one occasionally. They did it last semester. I think they'll probably do it again in spring or later. But that's the only way is to challenge CIS1A. And if not, you can wait to take it another time.
Can you hear me?
Yeah, I just saw your chat coming through right now. Who told you to email me today?
So I emailed them yesterday, like you had suggested, and then they told me that I have to go to the live lecture or the live counseling thing. And so I went to the live counseling today, and the counselor told me that they're going to email you to have the specific
professor take care of it.
Well, no, they're gonna email the department so they could. But then they said they were going to email you so that it can be approved, and then I would be able to add the class under this with the add code. But I've been trying to add the class with the add code, and it's still kicking back the same thing. So I didn't know if you've received the email or not.
I will check. I think they have to override something, but you know, I think people are not knowing the process because this is not a common process. So like when I started asking questions, I get like pointed to all different areas. So like they said, oh, well, tell the students to go to the counselor, but then the dean told me that you guys are supposed to fill out the form. So I will touch base with the CTE or the counselors and then find out what I need to do. If you have some kind of proof saying that you took that class elsewhere, then I just take a look at that and tell them whether it's equivalent or not. If you challenge the class, then they have to give you the test and then take that score and put it in the system as equivalent to CIS1A.
Oh, so they were using, because I took your CIS 18A class last semester, and since CIS 1A is the advisory for that, and I passed 18A, they were going to use that.
Okay. Yeah, I'll touch base with them. Thank you for that. But sometimes they don't get to the email right away, but I'll get on it and find out what they need to do. I just got to make sure that the system sees that you did it So because, you know, right now they tell you to add and you can't add. So I got to make sure I ask them how to get that done for you. Okay. And then I will get, you know, once you add it, you will see the material and you can turn it. We only did like print functions so far with like using idle and install Python 3. So you get to it quickly. It's really easy right now.
All right, I'll check with the counselors tomorrow as well.
Okay. Thank you.
Thank you.
Mm-hmm. Eric, you have any questions? Okay, Eric. I hope you have a good night. I'm going to sign off if you don't have any questions. Thank you. All right, you too. Take care. Bye.